All right. Today I want to talk about CRCs, cyclic redundancy checks. Motivation for this, just to give a little background, I bought this controller a while ago. It's a little Xbox controller. It's got a couple paddles on the back. Wow, means that I can play Fortnite and have a little extra buttons for my little thingies. Exciting stuff. But the problem with this controller is that the paddles are kind of remapped in firmware. So this is meant to be used like with a proper console, right? And so you're on your Xbox, you plug it in. Your Xbox doesn't know how to process like buttons that aren't the Xbox buttons, right? So the controller firmware says, okay, let me take this paddle and remap it to like the A button, and let me take this paddle and remap it to the B button. Wow, that way I can keep my fingers on the sticks, right, without having to take my thumb off to press the other button. Wow, exciting stuff. But I don't have an Xbox. I have a computer, and computers can handle lots of buttons, lots more than the like 12 buttons that an Xbox has, right? And so it would be nice for me if I could bind the back paddles to something like my push to talk key or something, or like some Discord action or something, right? Something that's not like just another act. I don't want to, or even just another controller button, right? I don't necessarily want to have to sacrifice one of the front buttons to have access to a paddle button, right? It should be its own thing. And so I've been kind of on this quest to reverse engineer the firmware of this thing. I download the firmware package, try to look at like entropy, bin walk it, etc. Nothing really interesting in like the firmware package that I can get from the internet. Probably it's like encrypted in some way or something, right? So we pop the bad boy open. Pop it open, and we see this thing is probably the brain of the chip or the brain of the controller, but I can't find this chip online, but I can find this chip online. I found this, and I not only can I find it online, I actually bought some of these things so I can play with them. And this thing is EEPROM, essentially. So it's a storage for the controller that is controlled over I2C from the brains, which is probably here. And we're hoping that if we were to like pull the flash off the controller and dump the contents of it, maybe we see something interesting. Maybe not, but it's our only lead right now. And so, in an attempt to accomplish this, I bought, let's see if I can hold it with the camera without breaking anything. I bought this guy, little Raspberry Pi Pico. He's, the world's, he's a really cheap, stupid microcontroller, cost like $7 Canadian, and I can like talk I2C over that thing, which is really the only important part here. And now we look at this thing, we start going on some side quests, right? They ship an SDK. Fuck that. We don't want to use their SDK. We want to do it the hard way, right? So we're starting to like look through the boot process. We're looking at their hardware data sheets, and we started looking at bootloaders the other day, right? So the chip, he starts with some pre-programmed read-only memory that like comes on the chip that runs bootloader stage 1. Right? Bootloader stage 1, he looks at the flash on the chip and he says, hey, have you programmed me with something? If so, let's run it, right? So he tries to run bootloader stage 2. But in order to check if bootloader stage 2 is there, he looks at the first 252 bytes of what's on the onboard flash, and he goes, hey, do the next 4 bytes indicate that the first 252 bytes are sane? Right? And the way he does that is through a circular redundancy check, CRC32. And so we, the SDK would normally do this for you, right? But we, doing things, the hard way, go out of our way to try to do this CRC checksumming of the bootloader ourselves. And you look at this and he goes, the parameters of the checksum are polynomial, sum hex number, input reflection, output reflection, no, initial value, XFFF, final XOR, 0. What the fuck are we talking about, dude? Polynomials? Why are we talking about polynomials? This is just a fucking number, right? And so that sent us on this little side quest to look at CRCs. And it turns out these guys are used all over the place, right? These guys are used in like, they're used in the data transfer protocol for you and your hard drive. They're used in like every compression algorithm ever. They're used in like PNGs. They're used in Ethernet frames. Your router is checking the packets that come in over the internet are okay by running this CRC. They're used in file systems, right? Your ext4 Linux drive is CRCing your files to make sure that like when there's bit rot that it can tell the difference, so that it can notice that something happened, right? And so here we're seeing again, what the fuck is this? Why is there like x to the 32 plus x to the 26 plus x to the 23? What the fuck are we talking about? Right? And so I was trying to like decipher this Wikipedia page, and they give like a pretty good like level 1 explanation, I think, here. But trying to get from here to the final answer that was like something that was usable to implement like a real CRC32 check was not trivial, and so I thought it was worth going over. So let's talk about it. CRCs. To talk about CRCs, we first have to go back all the way back to like grade 4 and talk about long division, right? I'm only saying this because I started looking at this and I was like, how the fuck do you do long division? I haven't done this in like 25 years, so I don't remember. But recap. You got small number, 57. You want to divide this into big number, 1100 and, maybe like 1, 2, 4, 7 or something, right? You draw it like this, right? You go 1, 2, 57 divided by 57, and you start taking the 57 and you go digit by digit, left to right. You go 1 is 1 bigger than 57? No. Is 12 bigger than 57? No. Is 124 bigger than 57? Yes, let's go, baby. How many times bigger than 57 is it? Well, probably 2 times, 3 times. 3 times would be 15, 2 times would be 10, so no, 2. And then you do the multiplication. You go 2 times 57, 10, just kidding, 114, I think. 2 times 57, 114. That sounds kind of right. Then you like subtract this shit, right? Boom. You get, what do you get there? You get 0, 1, 0, 7. And then how many times 57 go into 1 is 7? Probably twice? Once? So, right, so you do 57 here, subtract, hello, fuck you, Vim. And then at the end you get 10 minus 5 is 5, 0. 50, so 21, remainder 50. I think that's right. We can do a quick like sanity check here. We get 1247 out of 57, 21.8777. Remainder 50. Yep. Okay, cool. 21, remainder 50. Okay. You might think, Mick, we don't fucking have to talk about long division. I'm not stupid. And I would go, but I was. Okay? And this is a building block for the next thing. Okay, so long division, simple, right? Now we get into this thing, polynomial long division. We'll explain it. We'll tie it all back in a minute, but let's just say that we want to do polynomial division. So we say maybe we want to take some polynomial, x to the x cubed, maybe like 2x cubed plus 4x squared plus 1, right? Something like this. And you want to divide this by x plus 4 or something, right? Well, it turns out this is the exact same fucking thing, right? You multiply, you look at the big thing first, you go 2x cubed. How do we get that bad boy out of the way? And you're like, 2x cubed, x times 2x squared probably gets us there, right? 2x squared times x is 2x cubed plus 2x squared times 4 is 4x squared. So this becomes, we picked kind of lucky numbers there. Let's change this to 5x squared so that we have some more work to do. Right? So then we end up, you do your subtraction, you go blum, 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 blum. You get 1x squared now, plus 1. You're like, how many times does x plus 4 go into that? Probably x times. Right? So you multiply by x, you get x squared plus 4x. You do your subtraction. You get the answer is what? Negative 3x. No, this is negative 4x plus 1 remaining, I think. You're like, how many times does this go into that? I guess negative 4 times. Negative 4 times, you get negative 4x minus 16. Then you get remainder, negative 15. Wow, we did polynomial long division, right? So this guy is the same, 2x plus 5x, or 2x cubed plus 5x squared plus 1 is the same as 2x squared plus x minus 4 times x plus 4 minus 15, right? This is what this tells us. And why are we talking about this? Well, it turns out that this minus 15, this is essentially what a CRC is. Hand wavy, right? A CRC is just the remainder of some polynomial division. And you might say, well, then what the fuck are we talking about here then? What is this 0x04c11db7? How is that a polynomial? Okay, one more concept to introduce. There are these things called, apparently they're called Galois fields. That's crazy. They're spelled like Galois fields. Finite fields, also known as Galois fields or Galois fields, right? And these polynomial divisions in CRC are done in Galois field 2. What does this mean? Okay, so let's like think about like typical number line. We got numbers, right? We're doing math. We got numbers. We got 0, we got 1, we got 2, we got 3, we got 4. How many numbers do you think I can list? Probably a lot. 5, 6, 7, 8, 9, 10, etc., etc. And then like on the, on the negative side, you get -1, -2, -3, -4, etc., 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 right? And what if we're like, we look at this number line and we're like, too many fucking numbers, dude. Too many numbers. I can't count that high. I have 5 fingers on this hand. I don't want to count higher than that, right? And so if we're like, okay, well, I only have 5 fingers. Let's work in Galois field 5 space, baby. And so what you do here is you're like 0, that's tool. I can count that on my thumb or my fingers. 1, that's my thumb. 2, finger and thumb. 3, another finger, another finger, another finger. Uh-oh, out of fucking fingers. So you go 6, fuck that shit. 1. 7, fuck that shit. 2. 8, 3. And the same thing on the other side. Like -1, I can't show -1 on my hands. Fuck that. We'll go back to 5. 4, 3, 2, 1, right? And so your number line just essentially starts looking like 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. And it turns out that this has like, some nice mathematical properties. You can define like multiplication and division in this space, right? So you can say like, instead of saying 2 divided by 3 is 0.6, 0.6, I don't have 0.6 of a finger to put up. I only have 1 finger at a time, right? So instead, you define it as the inverse of multiplication. Plus, so you go like, 2 times 3 equals 6. 6, no good. We don't like 6 around here. 6 is 1, right? So 2 times 3 is 1. And so you're like, well, division is just the inverse of that. So 1 over 3, that's 2. And 1 over 2, that's 3. Because 3 times 2 is 1, so obviously going the other way, you have the same stuff, right? And my understanding of this, which could be wrong, is that by defining these like Galois fields, you can use your typical tools of mathematics to make proofs, but in a way that like you're representing data that is like a little bit more useful to you, right? So when we're talking computers, 5 fingers, too many fingers. Computers only have 1 finger. Right? So we work in Galois fields, 1s and 0s. So your number line for a Galois field 2 is like 0, 1, 0, 1, 0, 1, 0, 1 forever. And so we'll go back to this polynomial division, right? Say we want to do this polynomial division, but in Galois field 2, right? So you're like 2x cubed, not allowed. That's now 0x cubed. 5x cubed, not allowed. 1x or 5x squared, not allowed. 1x squared. 1, that's chill. We'll leave that in. X is totally fine, but plus 4, not okay. Plus 0, baby, right? Because you're just taking like evens and odds, right? So now this becomes like this, and you're like, okay, so I multiply this by x. You do x, so do minus x squared, and I guess you just end up with remainder 1 in this scenario. Right? We could probably get a little bit more complex here, right? We could do like x cubed, and we could probably do like x plus 1 here to make sure that this is a more interesting division, and we could do x squared plus maybe like x cubed plus x plus 1 or something. Let's run this one, okay? So we need to multiply by x squared still. Boom. So we're like x cubed plus x squared. We do the subtraction, so we end up with what? Negative x squared plus x plus 1. We divide this in here, so we need to do -1 though. Not okay, right? -1 is just 1 because fuck numbers that aren't 0 and 1. Then it's like, okay, so we time plus x. Boom, boom. Then you get like x squared plus x that we're subtracting, and then we end up with remainder 1, right? Chill. Okay, so we're getting a lot closer to what CRCs are actually doing. Remember, we said that the remainder is the CRC. That's all we're going for, right? And so let's just kind of like rewrite this a little bit. if we just like took anything with an x out of here, first of all, let's like show the like x squared in here, and then let's just 0x squared is the same thing here, right? Times 0 is nothing. And if you just take out the x's, you end up with something that resembles a binary number, right? 1x squared plus 1x cubed plus 0x squared plus x plus 1. That's what we're fucking talking about here, right? So CRCs are doing a polynomial division, kind of representing a big ass polynomial as a set of bits. And what this lets you do is you do the long division, but all of your subtractions in this like long division world, wherever the fuck we were, these are the same as XORs, right? So let's kind of run this back with this representation, right? So 1-0 is x plus, I guess 1-1 is x plus 1, right? So we're like, okay, so we don't care about the result anymore. We're just gonna do like the division part. So here we would say we need to multiply by something to make it line up, right? So we take like the 1-1 here. This is essentially saying like we take our x plus 1 and we're multiplying it by x squared to get it to x cubed plus 0x. We do this subtraction, right? And we say, okay, so now we have 0x cubed and 1x squared plus x plus 1, right? And then we do the same thing. We say, okay, so we multiply this x plus 1 times x to get 1 here. We do the subtraction, 0, 0, 1, and we end up with remainder 1, just like we did before. And so this is kind of the heart of the CRC. The CRC parameter, the polynomial that they're talking about, is like the thing you're dividing by, and your input data is the input polynomial. So how does this relate to like letters and numbers, right? Usually when you have CRCs, you're like doing some checksum over some like real data, right? So we say we have like the string like hello, and we want to say, does this word hello have any like data corruption in it, right? What is he good? What's he look like? And so we want to compute the CRC over this thing. Let's jump over to visualization. So we say hello, right? We take the binary representation of each of these letters. Maybe we'll do hi because it's shorter, right? And we hand wavy, we like say, here is the H in ASCII, here is the I in ASCII, and this is going to be one big ass fucking polynomial, right? So we're gonna have like, this is 1, 2, 3, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So x to the 14 plus x to the 13 plus x to the 11 plus x to the 6 plus x to the 5 plus x to the 3 plus 1. Something like that, right? This is our input number. And we are dividing by some polynomial. In this world, we're going to say that our polynomial that we're dividing by is 1010. X squared plus, x cubed plus x. We just kind of keep doing this same thing, right? So we say, okay, we put the 1010, we line the 1 up with the 1. We try to get rid of that shit. We do our subtractions. XORs in this case, because XOR and subtraction are kind of the same in Galois field 2, right? And then we get our new number, and we go again. We say, okay, we'll put the 1010 here, boom, right? And we do this again. Okay, we have another 1 here, so we put the 1010 here, boom, boom. We do our subtraction, another 1 here, boom, 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 boom. And we keep doing this until we are only at the remainder, where we've intentionally padded our data, our input data high, with a few extra bits to say, this is going to be, like, we're just making sure that there's room for a remainder. And so we end up with this remainder, 0x squared plus x plus 0. And this is the CRC. Then what happens is on the other side, somebody else, they just run this same division again. They get the same number, and they're like, hell yeah, data's still good, baby. Yeah, and that's kind of like how it works at like a very base level, except no implementation does this, really. Like, nobody does this. And so I think it's helpful to reframe this as slightly differently. So let's just say that instead of going line by line here, let's just only ever show the last 2 lines, right? So we'll go here and we'll bring this number. We do, our first part of the division. So we find the first one, we drop the polynomial under it, we do our subtraction again, and then we'll take this number and put it up here and go again. Right, so when I go up next, we have this like 1, 1, 1. Now it's 1, 0, 0. I'm going to press next, and it's going to say 1, 0, 0. And we basically just keep going until we get to the same checksum, the same 0, 1, 0 at the end. Hell yeah, right? And looking at this, what you'll kind of notice is that we're kind of shifting. It feels like we're shifting the polynomial that we're dividing by kind of like right through the whole shebang, right? And on the left side of this thing, we're kind of leaving a trail of zeros. Right, we have like just a bunch of zeros over here. And so really, you can look at this and you can go, well, all we really care about in this is this like remainder at the end. And really like all of these zeros are kind of like wasted space, right? We don't really care about writing those down. It's almost like you could like fix, instead of sliding the polynomial to the right through the data, you could slide the data to the left over the polynomial, right? So we're going to switch to visualization number 2 here. So we're going to take the same text and polynomial. I think this is right. Polynomial is 0, 1. It was 1, 0, 1, 0 before, right? So I think it was A. And here we have kind of the same thing, right? We have our data here, high, padded with some zeros at the end for extra remainder space. We have the same thing where this data is just this data again, right? So we have like 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0. So this is the H, this is the I, and this is the like remainder. The only difference here is that we've padded this on the left side with 1 extra 0. And the reason for that is because we need space. Okay, if we go back to like the other visualization for a second, when we make it to the end of this thing, you'll notice that the input data is all zeros, right? And the checksum is 3 bits here, but our polynomial is 4 bits, right? And that's because we needed kind of like one at the end here that like leaks over the edge of the checksum section to finally clear out that last one in the initial data, right? So in this other visualization, we're kind of doing like the same thing here, where we're just padding this with an extra bit at the edge to make sure that there's room for the polynomial to do its like last step of division, right? And in the division case, we were kind of snapping the polynomial to any section where there was a 1 in the data. But if we start sliding the data through to the left here, we could like snap it to the edge, but we're not going to do that quite yet. I think it makes more sense to kind of visualize it like piece by piece. So here what we're going to do is every time we see a 1 in this slot, we'll do the polynomial division, right? Or we'll do the polynomial subtraction again, right? So this is like we're going, okay, we found a 1, we'll do our 1010, and we'll find out this goes to 111, this 111 snaps up, and we basically just keep doing that, right? We say, oh, there's a 1 here, time to do polynomial subtraction, boom, 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 and eventually we get to the same 0, 1, 0 at the end, okay? So this is kind of more analogous to how a typical CRC implementation would work, except that we're missing one piece which they call the initial value. Now, this thing took me a long time to figure out. In fact, even at like the end of last stream, we worked on this for like a couple streams, this visualization, this absolute trash Temu 3 blue 1 brown visualization, right? But we were really struggling with the idea of we were really struggling to like get the same answer as a typical CRC32 would. And it's because they had this initial value seed, or initial value. And what it does is we take our data here, hi, right? And we put it, we preload this like special section of where we're like looking at the end of the data. We call this like the register or whatever, the CRC register is what we've been calling it. And we just XOR the seed with that value. So I put in a seed of like F, right? This gets 111 here. We XOR that shit and it gets applied here. The first bit actually shouldn't count. This should be 7 is a better example here. Boom. right? So we XOR this becomes 1, 0, 0, boom, and then we carry on like normal, right? We're chilling. We're done, boom. We might want to increase the size of the polynomial. So a CRC32 wants 32 bits of CRC data, which means that they use a polynomial that looks kind of like this. Right, so if we take this polynomial that they put in here, like this, we actually, this is not the right, they're kind of cheating. They're kind of cheating, right? If we count up how many bits of CRC we get, it's basically like one order less than the highest set bit here, right? Right, we were saying before that in this case where we had like a, this 1101, we need to line up the biggest one in this guy with this leftmost field here so that we have 3 bits of CRC data, right? Because we're trying to clear out all of the initial data and end up with some extra data at the end. The extra data at the end is the remainder, the part we're interested in. So if we want a 32-bit CRC, then we need something that has x to the power of 33 in it. And you'll notice that this number they give us is a 32-bit number for a 32-bit CRC. So that means that you can't possibly express x to the power of 33 because you need 1 bit per power plus like the constant one at the end. And so what they actually mean when they say this is they actually mean throw a 1 in front of this thing, right? There's an implicit 1 because we don't have to, like every single polynomial will start with x to the highest power that it can, right? So every 32-bit CRC will have an x to the power of 33 in its polynomial. And so they actually mean this, where you put a 1 in front, right? This is actually what they mean. And then if we count up how many bits we get here, it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 25, 26, 27, 28, 29, 30, 31, 32, right? So we have a 32-bit CRC here. And if we did the thing where we feed this all through and we seed it with, the F that is typical here, we should end up with a correct answer at the end of this. Now, this is hard to interpret now. As we get into bigger and bigger numbers, it becomes harder and harder to interpret. So we can kind of flip into a C implementation of this thing, which is pretty straightforward. Can we, with syntax highlighting, this is probably fine, right? So this is kind of the C implementation of this, right? So we go, okay, we got some data. Maybe we write hi in here. We have our polynomial, we have our seed, right? We go, okay, let's read the first 32 bits from this thing, right? We're trying to make a 32-bit CRC. So we read the first 32 bits, we apply the seed, and then we do the rest, right? So we say, is the highest bit of the register set? If so, that means we need to do an XOR after shifting in the latest bit, right? Simple. And if we run this guy, we get this number, which if we compare with Zig's implementation of CRC32, I think that we don't have the same. What did we type in here? We said hi. So I guess that means in our Zig implementation, we should also write hi here. So here we are using Zig's standard library thing here with the polynomial that we wanted to use, the seed of a bunch of f's, and then kind of like null parameters for the other stuff. But we do see this, which looks different. Did I get the right parameters here? Hi, a bunch of f's. Oh, here. I forgot to write it too. There we go. Okay. So Zig standard library is giving us this number, which is the same as this number. Hell yeah. We fucking got there. We got an implementation. But what the fuck is what up with these parameters? Well, it turns out that some implementations expect maybe they expect the bit order to be different, right? So we're kind of working under the assumption here that the highest bit here, like, is if we were to take the the binary representation of the letter H, which is what? We have an H here, so it's hex 68, right? We're assuming that the highest, most significant bit in the binary representation of hex 68 or whatever is the first thing that gets shifted in to the register, right? We're assuming that we're going this bit, then this bit, then this bit, then this bit. But some implementations actually expect to go the other way. They expect to start with this bit, then go 0, 0, 0, 1, 0, 1, 1, 0, right? Go right to left, but still kind of like parse the data left to right. So there's options for, reflect input and reflect output here, wherever the fuck we were. Reflect input, that's what they're talking about there. In some implementations, you might see that as the polynomial being flipped, right? If you look at the CRC table here, they have, well, I guess the header is probably the useful way to look at this. They have reversed and reciprocal, right? So depending on your implementation, you might be using any one of the like reversed or reciprocal, like like I guess the inverted version, or reversed reciprocal. You might be using any of these. Depending on if you're like expecting to reflect your input, or sometimes your output also wants to be bit reversed for some reason. And then also for some reason, implementations might just take the number that you get out at the end and just like XOR it with something else, like just for shits and giggles. Don't know why. But this definitely the hardest part to grok for me was application of this seed value, right? Because they call it like initial value, and this is not an initial value, right? We're taking some input and XORing it with this seed, which is just kind of confusing. But it becomes less confusing if you look up like, let's ask ChatGPT for like, can you give me a CRC32 implementation in C, please? Pleases. Can we stop it? No table, please. Okay. This is kind of more analogous to an implementation you would get instead. This is confusing, right? You look over the data and you're like, wait, I thought we were shifting data into some register. So why the fuck are they XORing the data into the CRC, then shifting it, right? So my CRC, he's 32 bits, my data, 8 bits. We're just like, take the data, slap it in there, and then like start shifting the CRC and XORing it with the number. Okay, first of all, we're going to be seeing that they represented this the opposite way. They're shifting to the right instead of shifting to the left, and their polynomial is one of these other ones, right? The idiot decided to pick this one instead of this one. These are equivalent, but he's just represented it the other way. So his highest, you could imagine it that the highest power of x is on the right side of the number instead of the left. But the biggest confusion here is like, why is he doing this? And it turns out that through some, I think it's communicative property or something, the fact that like XORs, you can XOR over here, then XOR over there, and then it's the same as XORing in a different order because it's just flipping the bits. It turns out that this is mathematically equivalent to what we were talking about. And because of that, now the initial value of the CRC, that like seed value, is actually being just set there on the first line. And it's just something weird about like order of operations. It just turns out to be exactly the same thing. And so, but it just means that if you kind of got to the CRC implementation from first principles, you would not do, I don't think, you would not fill the register, then XOR it with a seed. That just feels weird, but it is what it is. Anyways, I just thought that was like kind of like a fun exercise. I was interested in it. I've seen CRCs pop up so many times, and I've always been confused about like, what the fuck are they talking about right now, right? But now we can look at this and go, okay, so the Raspberry Pi CRC that's running on the bootloader, they're expecting us to use the standard like zip polynomial, right? This is something that has an implicit x to the power of 33, but we're basically just going to be XORing our register with this number. We're doing no input reflection, no output reflection, and we are not XORing the final output with anything. Pretty cool. Pretty cool stuff. Anyways, I just thought that was interesting. It was hard for me to push through and understand, even at this level, which is not very well. But hopefully that was interesting. And if not, too bad. You've made it to the end, so you can't get your time back. Your life has been wasted. But for the rest of you, hope you enjoyed. We stream most days at 12:30 Pacific time to 4 o'clock Pacific time, working on whatever. We've been working on this Raspberry Pi dumping of Flash, so we'll probably be back on that tomorrow. If you want to check that out, you can swing by. Otherwise, the interesting parts of stream I try to post on this YouTube channel. And if you want to support and see kind of the we call the other half of the stream like happy hour. It's kind of stuff that is like less titleable and thumbnailable, but stuff that maybe like stuff that I think is still worth doing, stuff like refactoring, stuff like unit testing, stuff like reading. If you want to see kind of all that content, you could support on Patreon or on YouTube members or on Twitch, and you get access to all VOD content. So if you want to see that, swing by, catch us live, or subscribe, whatever. Do whatever you want. I don't care. And I'll see you guys around. Later.